Good morning, friends. First of all, I would like to thank the organizer for giving me an opportunity to present my topic over here. Today, I am going to discuss about symmetry and group theory. Let me introduce first. Myself, I am Dr. C.K. Modi, working as Associate Professor in Department of Applied Chemistry, Faculty of Technology and Engineering, the Maharaja Sayaji Rao University of Baroda. So this is my topic, symmetry and group theory. Let me start the topic. Now, what is symmetry? Symmetry means same. Now, what do you mean by symmetry? The term symmetry means a structure in which the parts which are in harmony with each other, as well as to the whole structure. Now, while we concentrate on the nature, there are countless examples of symmetry, like flowers, leaves, animals, etc. Look at this example, butterfly. Now this butterfly, which is symmetrical in nature. So if you draw a line which passing through the center of this butterfly and it divides into two parts. Now both these parts which are mirror images of each other. Now this part which is mirror images of this part. Okay, therefore it is symmetrical in nature. Now few more examples of symmetry, like these human faces. Now look at these human faces. While draw a line which passing through the center of this face, it divides into two parts and both the parts which are mirror images of each other. Same way, look at this insect which is also symmetrical in nature. Apple which is also symmetrical in nature. Now this is a vertical line. Now when the vertical line passing through the center of that molecule and it divides into two parts and both these parts which are mirror images of each other, then we can say that it is symmetrical in nature, right? Now horizontal lines. Now look at some of the examples of scissor, bow and arrow, and this ladybug. All these examples in which when we draw a line passing through the center from side to side and it divides into two parts and both these parts which are mirror images of each other, and therefore we can say that it is symmetrical in nature. So this is horizontal line, side to side. Now some of the examples, they would have vertical line as well as horizontal lines. So vertical symmetry and horizontal symmetry both are present. So it divides into two parts and both the parts which are mirror images of each other. So these are the examples where both vertical and horizontal symmetries are present. Now important thing, that is symmetry elements or operators. Now what do you mean by symmetry elements? Now symmetry elements, these are nothing but the imaginary geometric entities. So these are nothing but the symmetric geometric entities. They might be points, lines, and planes. So when we perform any symmetry operations, So after performing that symmetric operations, the molecule gives an indistinguishable configuration, or we can say that an equivalent structure. So all symmetry elements leave the molecule in an equivalent positions, or we can say that indistinguishable before and after the operations has been performed. Now look at this example, like hydrogen molecule. Now while performing that symmetric operations, if we carried out any symmetric operations, after performing that symmetric operations, if we get equivalent structure, okay, then the molecule have the symmetric operations. Look at this hydrogen molecule. Through the centers, if an imaginary axis passing through the center of that molecule, and this imaginary axis, if we can rotate at around 180 degree on z-axis. So if I consider as z-axis, if I rotate at 180 degree, after 180 degree rotations, what will happen? What will happen? So this H prime comes over here and this hydrogen comes over here. Therefore, they interchange their positions. Now this structure which is equivalent to this structure. Therefore, we can say that this is equivalent orientations. Therefore, this molecule have symmetry. So this is cyclic operations which we have performed on z-axis. Now symmetry elements. Now generally there are 5 types of symmetry elements are present. Now these symmetry elements are like identity, which is symbolized by E, axis of rotation, that is symbolized by Cn, or which is also referred as cyclic rotation. Okay. Third one, that is called as mirror plane, which is symbolized by sigma. Fourth one, that is called as center of symmetry or inversion center, which is symbolized by I. And the last one, that is called as improper rotation, or which is also referred as rotation reflection axis, which is symbolized by Sn. So we shall discuss one by one. Now first one, that is identity. Now what do you mean by identity? Now identity is the operations where if you perform such operations, after performing such operations, you will get that equivalent structure. No change is made in the molecule. Okay. So after performing identity operations, no change is made in the molecule. The molecule will remain as it is. So an operations which brings back the molecule to its original orientations. Identity is present in all molecules and compounds. So if you imagine any compounds molecule, they all possess identity E. Now the next element, that is called center of symmetry, I. Now center of symmetry I, look at this definition. An imaginary point in the center of that molecule through which reflection of each atom can be performed. So suppose if I if I started my journey from this atom through the center of that molecule on the other side of an center at the same distance, if I find the same atom, then the molecule have center of symmetry I. Okay, so it is nothing but it is an imaginary point which is situated in the center of that molecule, around which the reflection of each atom can be performed. So after performing operations, we'll get the same atom. For example, if I started my journey from point A through the center of that molecule, this is the center of that molecule, on the other side of a center at the same distance, if I found like the same atom, then the molecule have center of symmetry. So this is the example of dimethyl mercury. This is methyl group. At the center point, mercury is there. On the other side, another methyl group is there. So A atom, that is nothing but hydrogen. So if I started my journey from this hydrogen through the center of that molecule, while extended on the other side of that center at the same distance, if I find this another hydrogen, so both these hydrogen, they are mirror images of each other. Therefore, we can say that this molecule have center of symmetry. Another example, this is carbonyl, chromium hexacarbonyl. Now this chromium hexacarbonyl, which also have center of symmetry. Now third operations, that is called as axis of symmetry or rotation axis. Now this rotation axis, which is symbolized by Cn. C stands for cyclic rotation and N stands for number of fold. Now rotation axis is an imaginary axis. Okay? These operations where we have to imagine. Now this imaginary axis passing through the center of that molecule around which the rotation can be performed. So after performing such operations, cyclic operations, if I get the indistinguishable structure, then the molecule have the rotation axis or axis of rotations. Now for 2 pi by n rotations, there is an n-fold axis of symmetry, which is denoted by Cn, cyclic rotation. Now look at this example, that is water molecule. This is oxygen situated at the center of that molecule. This is hydrogen, these two hydrogen, and it has actually bent structure. Now this hydrogen water molecule, which has any rotation axis is present or not? Let's check. So if I can draw an imaginary line which is passing through the center of that molecule, and if I can rotate this imaginary axis at around 180-degree rotations. So after 180-degree rotations, what will happen? This H2 comes over here and this H3 comes over here. So they interchange their positions. So after 180-degree rotation, what will happen? H2 and H3, they interchange their positions. However, oxygen, which is situated into the axis, therefore their positions remain as it is. So this structure, which is look like the original structure, or we can say that this is equivalent structure or indistinguishable structure. indistinguishable structure. Therefore, this water molecule has rotation axis. Now we have carried out cyclic rotations at 180-degree rotations, cyclic rotations. Therefore, so what is the value of this rotation axis? Now total degree of freedom, that is 360. Total degree of freedom, that is 360. And we have performed 180-degree rotation. Therefore, my answer is 2. So therefore, this rotation axis, which is considered as C2. So n is nothing but number of fold. Now, how can we get the value of n? So total degree of freedom, that is 360 degree, divided by 180, because we have carried out the operations, cyclic operations, 180 degree. So after 180 degree, we can get the equivalent structure. Therefore, 360 by 180, my answer is 2. Therefore, this rotation axis, which is symbolized as C2. So therefore, we can say that we can perform a twofold or 180-degree rotations to get the identical arrangement of the atoms. Now another example, BF3 molecule. Now this BF3 molecule, whether this molecule have rotation axis or not. So if I can pass imaginary axis through the center of that molecule, this is the center of that molecule, and if I can rotate at around 120 degree. So after 120 degree, what will happen? These atoms comes over here, these atoms comes over here, and these atoms comes over here. So they interchange their positions. So after performing cyclic rotations at around 120 degree, will get is indistinguishable structure. So look at this structure. So the red mark F, after performing 120 degree rotations, whether clockwise or anti-clockwise, so it is clockwise rotations. So this fluorine comes over here, and this structure, which is indistinguishable to the original structure. Therefore, we can say that BF3 molecule has rotation axis. Now, what is the value of n? Because we have carried out 120 degree rotations. So after 120 degree rotations, we'll get the equivalent structure. Therefore, total degree of freedom, that is 360, divided by, we have carried out 120 degree rotation. Therefore, the value of n is equal to 3. Therefore, this rotation axis, which is symbolized as C3. So BF3 molecule has C3 axis is present. Now some other molecule like BCl3 also has C3 axis. Ammonia, which also has C3 axis. Threefold rotation, that is called threefold rotations. Look at this. Now, BCl3 or BF3 molecule, it has, what is the shape of that molecule? The shape of that molecule is trigonal planar. Now, this trigonal planar, this molecule which consists of C3 axis along with some other subsidiary axes are also present. Look at this. This is my C3 axis. Okay, if I can rotate at around 120-degree rotation, after 120-degree rotations, all these atoms interchange their positions, and therefore this is C3. Now this molecule also have some other rotation axis. Now if I can draw imaginary line passing through, look at this. If I can draw an imaginary axis passing through any fluoride atoms and boron atoms, and if I can rotate at around 180 degree. So after 180 degree rotations, what will happen? These two atoms interchange their positions. However, this boron atom and this fluoride atom, they are situated into the axis. Their positions remain as it is. However, these two atoms interchange their positions. Therefore, after 180 degree rotations, these two atoms interchange their positions. Therefore, we can say that this is equivalent structure. So 180 degree rotations, therefore 360 divided by 180. So this rotation axis is considered as C2. Okay. Same way. If I can draw an imaginary axis passing through this fluoride atom and boron atom, and now if I can rotate at around 180 degree rotations. So after 180 degree rotations, we'll get the equivalent structure because this fluoride and this fluoride interchange their positions. So this is another C2. Same way, the third C2, it passes through this fluoride atom and boron atom. And after 180 degree rotations, we'll get these two atoms, these two fluoride atoms interchange their positions. Therefore, we can say that this is also considered as C2. So how many C2s are there? There are 3 C2. 1, 2, and 3 C2. And this is also C3. So total number of how many number of rotation axes are there? So here, 1 C3 is present. 1 C3 is present and 3 C2s are also present. So this is BCl3, BF3 molecule which has a trigonal planar structure. So it consists of C3 axis along with 3 subsidiary axes like C2. Now out of them, which one is considered as principal axis? So those axes which has n value higher. So, but naturally C3 is considered to be a principal axis and 3 C2 which are considered as subsidiary axis. Now rotation axis. which is also referred as proper axis of rotations, which is symbolized by Cn. Now, when n value is equal to 2, that is 180-degree rotations. N is equal to 3, that is called 120-degree rotations. N is equal to 4, that is 90-degree rotations. N is equal to 6, therefore 360 by 60, therefore 360 by 60, therefore n is equal to 6, and n is equal to infinite. So infinite degree of rotations. So there are various C and axis. Either n is equal to 2, either n is equal to 3, n is equal to 4, n is equal to 5, n is equal to 6, or sometimes n is equal to infinite. Now look at this example. This is a square planar molecule, NiCN4, for example, or PTCl4. Now PTCl4 is a square planar complex, or NiCN4 2 minus ion, which is also considered as having square planar geometry. Now this square planar molecule, which consists of now if you draw an imaginary line passing through the center of that molecule, and if I can rotate around 90 degree, so after 90 degree rotations we'll get equivalent structure. So therefore this is considered as 360 by 90, therefore which is considered as value is equal to 4. This is considered as C4. So this is C4. So one C4 is also present, and other subsidiary axes are also present. So look at the other subsidiary axis. There are 4 C2s which are also present in square planar molecule. So which one is considered as principal axis? Now those axes which has n value is higher. So but naturally this C4 is considered as principal axis. Now I have to stop my lecture over here. This is the part 1. I will